Almost everything, every electronic device in the world of technology needs a CPU to work. Each laptop, smartphone, computer, and even some cars need CPU, and it is a crucial thing for most of the technological devices. But the question is how these CPUs are made. What is their creation process? These are the questions that we will find out in this video. So stay tuned. Section 1. CPU Design and Planning. The journey begins long before any silicon touches a wafer. Expert engineers utilize advanced computer-aided design CAD tools to develop a detailed blueprint of the CPU. This phase defines the architecture, instruction set, and layouts for billions of transistors. Rigorous simulations help ensure that every circuit and pathway perform as intended. With such intricate planning, even the smallest error can ripple dramatically in performance and functionality. Advanced design techniques, including machine learning-driven optimizations, now contribute to creating ultra-efficient and powerful processors. Section 2. Making the photomask. After finalizing the design, the next step is crafting the photomask, a precision-made quartz plate that embodies the image of the CPU circuitry. This mask is the master template used during photolithography to transfer the design onto the silicon wafer. Every detail, from the smallest line to the most complex curve, is etched onto the mask to mirror the intended design. Such precision is crucial since any deviation can compromise the functionality of the finished chip. Section 3. Silicon wafer preparation. At the heart of every CPU lies the silicon wafer. These wafers originate from ultra-pure silicon crystals grown using processes like the Czochralski method. The crystals are then sliced into thin, circular substrates and polished to achieve a mirror-like finish. Before any further processing, the wafer is meticulously cleaned and oxidized to remove impurities and form an ideal surface for subsequent layer depositions. This pristine preparation is essential for success in the following nanometer scale processing steps. Section 4. Photolithography, patterning the CPU. Next, we bring the design down to the micro scale through photolithography, the process responsible for printing the CPU's intricate patterns onto the wafer. The wafer is first coated with a light-sensitive material known as photoresist. Ultraviolet light is then directed through our photomask to expose selected areas on the wafer. Advanced techniques, including extreme ultraviolet, EUV lithography, are used for nodes below 10 nanometers, allowing manufacturers to achieve finer resolutions with precision previously thought impossible. Once exposed, the wafer undergoes development to remove either the exposed or unexposed photoresist, leaving behind the exact pattern of the CPU circuitry. Section 5. Etching, doping, and transistor formation. With the desired pattern now on the wafer, the next vital stages, etching, doping, and transistor formation, begin. In the etching process, chemical or plasma etching precisely removes unprotected silicon, sculpting the intricate pathways and features of the circuit. Simultaneously, the wafer is doped through ion implantation, where specific ions are driven into the silicon to adjust its electrical properties. Modern CPUs often adopt advanced 3D transistor structures like FinFET or Gate-All-Around (GAFET) architectures. These designs, which offer improved power efficiency and performance, require highly specialized deposition and additional etching steps. Techniques such as chemical vapor deposition (CVD) and atomic layer deposition (ALD) are employed repeatedly, along with interim cleaning and oxidation, to build and refine these transistor features atom by atom. Section 6. Building metal interconnects. After forming the transistors, we need to connect them to form working circuits. This involves the deposition of thin layers of metals, typically copper, that serve as the interconnects linking billions of transistors. Multiple rounds of photolithography and etching define these interconnects, while additional deposition techniques lay down dielectric and barrier layers for insulation. Critical to this process is chemical mechanical polishing, CMP, which levels the surface between layers, ensuring that subsequent depositions occur on a uniform base. Manufacturers also integrate yield enhancement techniques and redundancy checks during this stage to maximize the number of fully functional chips per wafer. Section 7. Dicing, packaging, and testing. With the wafer fully processed, the next step is to separate it into individual chips, known as dies. This dicing process is carried out with precision to avoid any damage to the extremely delicate circuitry. Following dicing, each die is packaged in a protective casing that allows for integration onto printed circuit boards. This packaging involves tiny wire bonds or solder bumps that ensure electrical connectivity. Finally, every chip undergoes rigorous testing, ranging from functional diagnostics and speed benchmarks to quality and reliability inspections, to ensure that only chips meeting the highest standards reach the market. These final yield enhancements help secure the performance and longevity of each device. From the spark of a designer's initial concept to the billions of meticulously crafted transistors on a silicon wafer, the journey of a CPU is a testament to modern engineering excellence. This incredible process, enhanced by advanced lithography, innovative 3D transistor architectures, and sophisticated deposition methods, makes the digital age possible. If you enjoyed this comprehensive behind-the-scenes look at CPU manufacturing, please hit the like button, subscribe for more deep dives into technology, and let us know in the comments what topic you'd like us to explore next.